Welcome back to Finite Element Methods, Math 574. This is class number 10. So we've been talking about the 2D finite element method, and the last thing we talked about before we ended was how to keep track of our mesh in 2 dimensions and how, well, we didn't really talk about this, but how we're going to use that information to be able to assemble our stiffness matrix and our force vector. That's going to be the subject of this class and a few classes after that. I have to tell you why the structures that I introduced at the very end last time are kind of important for what we're interested in doing. So that's the idea. So let's take as a starting point the place where we ended last time, where we had a 2D mesh which looks something like this. So how many triangles are in this mesh? Well, there's 9 squares, each cut into two, so it's pretty easy to see that there are 18 total triangles. How many degrees of freedom are in this mesh? The degrees of freedom in this case, well, it depends on whether we're talking about piecewise linear or piecewise quadratic mesh. Um, if I don't say it otherwise, we'll just assume that it's piecewise linear. Okay, so only the vertices are the degrees of freedom in the piecewise linear case. And it depends on whether or not we're talking about a problem that has degrees of freedom on the boundary. So we've been talking about the model problem. The model problem is, just in case you've forgotten, it's minus Laplacian of u equals f, and that's in the domain, and u is equal to 0 on the boundary. And since u is equal to 0 on the boundary, that eliminates degrees of freedom on the boundary because we just set the value of the function, the solution, equal to 0 exactly. So there's nothing for that function to do there. And so that's why we say the degrees of freedom on the boundary are eliminated. So that's the case of the model problem. It's important whether we know we're talking about the model problem or not to make the following assumption. We'll number the degrees of freedom which are definitely in the interior. We'll number those first. And that's the convention we're going to take here. So these degrees of freedom in the interior are 1, 2, 3, and 4, but there are additional degrees of freedom on the boundary. 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this little example gives a false sense of reality. It makes it look like there are a lot more degrees of freedom on the boundary than there are in the interior. That's not generally the case. This is only for this very simple example where we have a mesh which is not very large. If we have a mesh which is got 1,000 squares in the x direction and 1,000 squares in the y direction, each of which gets cut into two triangles, then we have a lot more interior than we actually have on the boundary. Nevertheless, we're going to use this example to try to motivate things where we've got our numbering correct in the interior. So we number those first, and then we number our boundary points, which in this case happen to be a lot more than the interior points, just for this simple example. So we came up with these two arrays. So the first array was the coordinate array, and we just keep track of the x and y values of the interior vertices first, and then the boundary coordinates, the coordinates of the boundary vertex points next. And so there was a lot more of those, and they number with indices 5 up to 16. Okay, so those are just the x and y coordinates, or the one and the two, the first and the second coordinates for those points. But there's two things going on here I want to really emphasize, and that is we're going to keep track of the coordinates, but more importantly, we're going to number this so that the degrees of freedom in the interior are numbered first, and the degrees on the boundary are numbered last. Secondly, we talked about this so-called local to global node mapping array. So this T array, it's an array of numbers. How many, how big is it? Well, it has 18 columns, and 18 is exactly the number of triangles in your mesh. So there's 18. So what we're doing is each column represents a different triangle in the mesh. Okay, 1 up to 18. If I look at the triangles, what these entries are recording is the global degrees of freedom. So in row 1 for triangle 3 is where? Triangle 3 is here. So in row 1, we have the element 6. In row 2, we have the element 7, or we have the number 7. And finally, in row 3, we have the number 1. Okay, so the row number tells you the local degree of freedom in this triangle. So the local degree of freedom here is 1, 2, and 3. 1, 2, and 3. So this is telling you how the local degree of freedom, number 1, corresponds to the global degree of freedom, 6, and how the local degree of freedom, 2, corresponds to the global degree of freedom, 7, and the third one corresponds to the global degree of freedom, which is just 1. So 6, 7, 1, 6, 7, 1 for triangle 3. All right. So now, again, it's very important that we've numbered these interior degrees of freedom 1, 2, 3, and 4, because we're not going to really be interested in any of the degrees of freedom that are greater than 4. So, for example, all these degrees of freedom which are greater than 4 in their numbering are going to get discounted whenever we're dealing with the model problem. Okay, once again, T gives the local to global mapping of vertices. It tells us how the global vertices are connected to the local and vice versa. So let's look at triangle 10. What does the entry mean in T for triangle 10? Well, triangle 10 is precisely column 10 information. Now these labels here are not included. So that anything below this dotted line is not included in our array. That's because it's redundant information. I don't have to keep track of the row number, which I've dropped. There's 1, 2, 3 rows, and there are 18 columns. I don't have to keep track of that information. I'm simply putting these numbers below here so to remind you that this is triangle 14. It's a little bit hard to look at this and simply say, what triangle is that associated to? Because it's a little bit hard to see what column number that is. So for triangle 10, we're talking about these entries here. Remember, this is not an actual entry of my array, so really it's only 2, 3, and 4. What does that mean? It means the local node number 1 is connected to the global node, which is number 2. Local node number 2 is global node number 4. Local number 3 is global number 3. So if I put in T, if I ask it what is the global node number of triangle 10 with a local node number 2, that's equal to the global node number 4. Okay, so 4 is our global node number. And what is 2? 2 is our local node number. And of course, this is our triangle number. Okay, so does everyone see what that information is saying? It's saying that the global node number that is associated to local node number 2 in triangle 10 is equal to 4. That's how you read that. So how does this help us assemble the stiffness matrix? So I have to explain. To do so, I need to tell you what are these so-called local Lagrange basis functions, the local Lagrange nodal basis functions, in fact. So I'm going to end up underlining these. So I want to define something which I haven't defined yet, psi1, psi2, and psi3. Remember, our global basis functions were denoted by by phi, right? So phi 1, phi 2, phi 3, phi 4, 5, 6, 7. Those are the global Lagrange nodal basis functions. But we also have something called local Lagrange nodal basis functions. So I'm going to talk about the piecewise linear case first. Piecewise linear means that R is equal to 1, if you refer back to our last lecture. All right, so first of all, let's suppose that we have, again, we're in 2D, so we're assuming that we have a polygonal uh, open domain. And if I say it's polygonal and open, that means it's, of course, a bounded domain too. And we have a triangulation of that, which doesn't have any hanging nodes. Now, I'm going to think about numbering these triangles in some order. It's not necessarily easy to number the triangles because you might have a fairly complicated mesh. For this example here, it wasn't so hard to number the triangles, right? I can number them 1 through 6, 7 through 12, 13 through 18. And there's a kind of order implied uh, by what I have drawn here. It's not always clear whether a nice ordering is going to be available to you for a generic triangulation of a polygonal open set. But let's suppose that you come up with some numbering. It might not be the best numbering, it might not be even sensible, but you can always come up with some numbering. And suppose they're exactly M triangles. So I equals 1 to M. Now let's look at the nth one, K equals Kn. And we're going to make 3 copies of this. Okay, so this triangle that we're talking about is just copied 3 times, exactly the same. Okay, so 1, 2, and 3. Same triangle, and I'm just going to put 3 different functions on it. And, well, why couldn't I just put them over the same single domain? It's because it gets cluttered. So in the first one, I wanted to find this thing called psi2. Psi2 is a piecewise linear function. Actually, it's not even piecewise. It's just a linear function defined on the triangle that has the property that at A1 and A3, it's equal to 0, but at A2, it's exactly equal to 1. Okay, so it has exactly the value 1 here. That's psi2. Psi1, it has the value of 1 at A1 and the value 0 at A2 and A3. And similarly for psi3, it's 1 at A3 and 0 at the other 2 nodes. Now, these nodes here, they're the global coordinates, but I've numbered them in such a way as I've numbered them via their local node number, okay? So these vectors are global coordinates in R2, so it's an X and Y. So X and Y here, X and Y here, X and Y here. But the way I've got them numbered is they're numbered with respect to the local degree of freedom. Remember, in the rule about local degrees of freedom is I have to number in counterclockwise order. And it doesn't matter what you pick as being the first vertex. And it doesn't matter, well, it doesn't matter if I take this one, or this one, but I have to thereafter, I just need to keep a convention, so I'm going to number them in clockwise or counterclockwise order. So these are my so-called local Lagrange nodal basis functions. And of course, they satisfy the usual thing that a Lagrange basis function satisfies, that is, psi I at aj is the Kronecker delta symbol, delta ij, which I think you've all seen before, right? It's the symbol it's actually a function that is 1 if I and j are equal, and it's 0 otherwise. Now, by the way, the Kronecker delta symbol is also, that's the elements, precisely, it's the elements of the matrix I, right? The identity matrix. So in this case, this is going to be the elements of the 3 by 3 identity matrix because there are 3 degrees of freedom and 3 basis functions. Right. So, okay, those are our local Lagrange nodal basis functions, satisfying this is what's called a Lagrange nodal condition. So now we're going to define for each triangle, and I should say it like this. So for each triangle, we're going to define what's called a local stiffness matrix. Okay, it's going to be a little 3 by 3 matrix, and it's going to be symmetric because we're interested in solving the model problem, and the model problem has this bilinear form associated to it. So for the triangle number n, for each triangle, we define a local stiffness matrix, and I'm just using the index n for the triangles. I could use little k, but that gets confusing with the large K. So we're going to use little n to be our subscript, not our subscript, but our index superscripted here for our triangle. This has the elements A, alpha, beta. The superscript n just represents nth triangle, where alpha and beta roam from 1 to 3. And the reason why it roams from 1 to 3 is because there are 3 degrees of freedom on each triangle for our model problem and in the piecewise linear case. All right, so these elements are defined precisely through this bilinear form. You integrate over the nth triangle. You integrate gradient psi beta dotted with the gradient of psi alpha. Okay, and you're integrating over just the triangle Kn. This is the so-called local stiffness matrix. Now, how does the local stiffness matrix help you obtain the global stiffness matrix? That it takes a little bit of practice and thinking in order to realize how this works, but I'm going to show you in just a second. For now, let's define one other piece of information. We'll get back to this local stiffness matrix bit. Let's define what we call the local forcing vector or the local load vector. And again, we're defining it for each triangle. N equals 1 up to capital M. We're going to define this little vector. Where does this vector live? This vector is an element of length 3. Now, I hope you've seen this notation before. This means a 3 by 3 matrix, which is also a symmetric matrix. This is just a vector, so there's nothing here to symmetrize or to say is symmetric or not. It's just a vector from R3. The components of that vector are precisely the integral over, again, just triangle Kn, just the nth triangle, of f against psi alpha. Okay, f sub alpha, and then psi sub alpha. This is called the local load or force vector. And again, I can use that to build the global force vector if I notice a couple of things. So I did a calculation last time where I showed you how integrating or calculating a global degree of freedom involves adding together a bunch of local degrees of freedom. So I'm not going to repeat that calculation, but you may have to go back and look at that to understand or to remind yourself what's going on. Okay, so now we're not going to say right now how this thing and this thing are computed. We're going to assume that they can be computed easily or straightforwardly for each triangle. Each local degree of freedom or each local Lagrange nodal basis function can be computed. Its gradient can be computed, and its integral, the dot product of these two things can be computed over triangle Kn. And I can do this without any problems whatsoever. So we're going to assume that that can be done. Later on, we're going to come back to actually how do you write a code for implementing that part. For now, we're just going to assume that these can be assembled, these little local stiffness matrix and local Force vectors can be assembled without any problem, and we're going to show an algorithm for using that information to calculate our global stiffness matrix. Okay, so remember we're solving the model problem, and so this stiffness matrix associated to this model problem, we remember, is going to be a symmetric matrix with n10 by n10 entries, or n10 rows and n10 columns. And remember, it's not just a symmetric matrix, it's actually going to be a positive definite symmetric matrix. The algorithm which I'm about to show does not take advantage of the symmetry. The algorithm that I'm about to show does not take full advantage of the symmetry that's inherent in this matrix. So we are going to do some stuff that are is a bit redundant and a little bit wasteful because we're not taking advantage of the symmetry. But I'm going to leave that part for you to worry about. How do I take advantage of the fact that this is actually a symmetric matrix and I don't have to actually think about the entries that are below the diagonal because those are the same as the entries that are above the diagonal? We'll get, I won't address that, but I'll leave it to you to think about. Now, how do we build this from local entries? Well, you have to think about what we talked about before. Whenever we talked about a, let's say 2815, this was equal to an integral over the support of 28 intersect 15. Usually I write it backwards because it makes sense to do. Right? And then what I do is then I break this into triangles. Maybe this has 2 triangles in it. Maybe it's got 10 triangles in it. I don't know how many triangles are in the intersection. I know there's a finite number of them, and I know I can always figure out that information from my mesh. That's weird. Let's see if we can get that. So for example, we want to calculate something like that, and we want to use the local stiffness matrices to do that. The idea is, well, once I break this into into these individual triangles, let's suppose that there are 2 triangles in the intersection here. Okay, so we're trying to calculate this, for example. And suppose there are 2 triangles in this intersection. Well, then I'm going to write this integral over the 2 separate triangles. Well, once I do that, then I just recognize, well, this node number 15 for the first triangle is going to be related to some local degree of freedom. And 28 is also going to be related to some local degree of freedom. Well, instead of thinking in this global way, can't I think about these triangles as being some local entity, and having computed these local stiffness matrix elements already, can't I use those to compute this guy? And the answer is yes, you can do that. And the way you do it is you're going to do it through summation. Remember, there's 2 triangles in this sum, and so I should have 2 separately computed quantities coming in and giving the final value of this entry. And so that's what's happening with this algorithm that we're about to go through now. First of all, we're going to set the global stiffness matrix and the local force vector. Sorry, screwed that up. Let me back up. Set the global stiffness matrix and the global force vectors to be equal to 0. Now, I'm writing these in terms of arrays in the same way that you would write arrays or array sections in MATLAB. So these are MATLAB style what are called array sections. So I'm hoping that you're familiar with MATLAB style. See if I can make a box here. There we go. So these use what are called array sections. So I'm not going to talk too much more about that. I hope you've seen MATLAB type of coding before, and you know what I mean when I say MATLAB style array sections. That's all I'm going to say about it. What this means is I'm taking A, and this is the column index, sorry, row index and column index, and I'm saying all rows from 1 to n10 and all columns from columns 1 through n10 must be set equal to the value 0. This is basically setting everything to 0. Similarly with this force vector, we start off by initializing everything to be equal to 0. The outer loop for our algorithm is going to be the triangle loop. We're going to loop over all the triangles, and our triangle index here is n. We go from 1 up to capital M, that's the number of triangles that we have. And then we're going to loop over what are called the local degrees of freedom. Okay, alpha 1 to 3, there are 3 degrees of freedom for alpha, and there are 3 degrees of freedom for beta. If T alpha n, so this means if the triangle n local coordinate alpha is gives us a global coordinate which is greater than n10. What does that mean? That means it's on the boundary. That means it's on the boundary. So this is going to be a boundary degree of freedom if this gets triggered, right? If this gets triggered, you're on the boundary. So you want to skip that because that doesn't come into play for our model problem. Okay, what does it mean to index a loop? It just means essentially go to the next value in that loop. If we don't index the loop, we're going to come into the beta loop. And beta is also going to have 3 degrees of freedom, beta of 1 to 3, representing the 3 degrees of freedom in the local stiffness or in the local in this triangle. Okay, so whatever triangle we pick, triangle N. Same thing here. If that global degree of freedom associated with that N and that beta are greater than N10, that means it's a boundary degree of freedom, and we want to skip that because it doesn't come into play with our stiffness matrix. Now, if I haven't indexed these two loops, then that means I've got a point, I'm in a triangle where we have a degree of freedom which is less than n1 and 0. In fact, the alpha degree of freedom and the beta degree of freedom are both less than n10, so that means they're both interior nodes. They're both interior vertices. So what I'm going to do is, keeping in mind how I compute this integral, I'm going to break it up into the two triangles. This is saying you've got a hit here for that global degree of freedom. The global degree of freedom might be 28 and 15. So this might be 28 and 15. So what we're going to say is if that's 28 and 15 and that's a viable degree of freedom, then I'm going to take whatever was previously in 28, 15, and I'm going to add on the contribution from the local stiffness matrix, A, alpha, beta, N. Okay? Now again, I'm not taking advantage of the fact that I actually have a global matrix which is symmetric, and I'm not taking advantage of the fact that the local stiffness matrix is symmetric. There are little pieces of code which can do that for you. All this really represents is the fact that I'm breaking this calculation up into the integration over multiple triangles. Okay, and so what we're saying is when we get a hit like this, okay, where these are actual degrees of freedom, that contribution on the local triangle is going to contribute to some global degree of freedom for the stiffness matrix A, the global stiffness matrix. And we're going to enter it in by adding it on to whatever was there previously. Of course, we start out by initializing it to 0, but whatever is there after this initialization process or after we've made some steps, we're going to add on this new information. And this just means we're going to add on a part of the integral to something that was already there. Okay, and then of course we have the end do for the beta loop. If you're more interested or more used to dealing with MATLAB, then this is a for this is what it's called, a for loop rather than a do loop. Um, and so you might see that in MATLAB is written as a for beta equal 1, 3, etc. But in any case, they're doing the same thing. A for loop and a do loop do the same things. How do I compute the global force vector from the local force vector? Again, it's going to be exactly the same. There's not two indices for a force vector, so there's only one index, and all we need is the alpha index in this case. We're going to take whatever is already there. Remember, this is just some global degree of freedom for triangle N, which has the local degree of freedom alpha. So this might be like 28. We're going to add what's we're going to take what's already there. It might be 0 or it might have already been updated. And then we're going to add in this integral calculation f alpha n, which was, remember what f alpha n was? It was just this guy. And we assumed that that can be calculated easily for every triangle. We assumed also that this can be calculated easily for every triangle. Okay, so that's the algorithm. That's how you use the local stiffness matrix and the local force vector to assemble the global one. It's going to take you a little bit of time and maybe doing and going through an example to convince yourself that this algorithm really assembles the global stiffness matrix from these local stiffness matrices. Okay, which I'm populating and counting, or which I'm populating in a kind of preconditioning or pre-processing step. Okay, what happens if we go back to this example? So I just wanted to fill in a couple of the numbers here. So for this example, M was exactly 18. That's the number of triangles. The number of interior degrees of freedom, interior vertices, is 4. The number of total vertices is 16. We're only going to be interested in those 4 in the interior, though, for the model problem, because boundary nodes are the ones that are indexed after the interior nodes, and they're indexed 5 and greater. So they aren't actually used in the calculation because what do I mean by degrees of freedom is eliminated? Well, this is already known to be 0, so we don't have to put that information in there. And I said, of course, this is our local to global mapping. And for example, what's the meaning of T214? So that means I take triangle 14, I'm looking at the second degree, local degree of freedom in there. And I don't know how this one's numbered, 14, but I think we can infer that pretty simply. So it's saying in here, the way I did it was the first degree of freedom for triangle 14 is going to be 15. So triangle 14, yeah, that's right here, right? So that means the local degree of freedom here is 1, and this is 2, and that guy's 3. So it should be 15, 3, 13. Did I get it right? 15, 3, 13. That's exactly what is the meaning there. For triangle 14, local degree of freedom 2 or 1 is 15. Local degree of freedom 2 is 3, and local degree of freedom 3 is 13. That's what all that information means. Let's do another example. Suppose I have triangles. I'm zooming in at some small part of a really big mesh. Okay. And so the fact that we're deep in the interior here. So triangle 16 is way in the interior. That's how you should view this. So that means the boundary is nowhere in sight. So for example, 20, 21, 22, 42, 43, and whatever the heck this guy is. Well, let's put a number on that. I don't know. Um, see, I think I numbered it later on. Did it for the quadratic case. Let's call this one 71. Okay. We'll just suppose that that's node number 71 for the vertices. Okay, so this one is piecewise linear again. What does piecewise linear mean? It means R is 1. We're piecewise linear polynomials. And now suppose we want to look at, well, what does the T mapping look like, the T matrix? Well, I'm going to give you the entries only for triangles 14, 15, and 16. And I skipped 20 because there are a few in between that. So 14, 15, 16, 20, and presumably triangle 17 is floating around. It might be over here, and that would mean this is a triangle 18 and 19 and 20, something like that. Okay, so for triangle 14, well, I've got the nodes mapped out here. So local node 1 should be global node 20. Local node 2 should be global node 21. And local node 3 should be global node 42. What about triangle 15? Local node 1 is 21. Then we have 22 and 43. And 16, 1 is 21, 2 is 43, and 3 is 42. Okay. And of course, these numbers are just the column numbers. They don't actually appear in this mapping. They're there implicitly. Now let's look at the assembly of A associated to with this mapping and how it's used. So suppose we're cycling through the triangles and we come to node or triangle number 16. Well, then we're going to do first alpha equals 1 and beta equals 1. We have two loops, and the first entries that we come to in those two loops is alpha equals 1 and beta equals 1. So T alpha n, so that's alpha is equal to 1 and n is equal to 16. So we're looking at entry 116. So 116, that means that global node is 21. And this global node is also 21 because beta is equal to alpha. So this means we're going to be updating global stiffness matrix entry 2121. And we're going to take whatever is already there and we're going to add to that the local stiffness matrix entry 1116. So 16 is my triangle number. Right? So now let's think about what is that guy? What is A2121? Well, it's A2121 is going to be whenever we're right, it's going to be this global degree of freedom here, and that's just a tent function. And the tent function has all these triangles in its support. So we're only adding the one element from K16 for 2121, which is contributed from that support over K16. So we're not doing K15 yet. That's in the support as well. And K14 is in the support for 2121. We're only adding in the contribution for 16. We previously added in the contributions from 14 and 15, and presumably these triangles as well. So there's something already in there, right? It's already buried in there. We're now adding in the contribution coming from 16. We've already added 14, 15, and these guys as well. So now we're adding in the last contribution for computing this A2121. That's that. Now, okay, let's index beta. So beta goes to the next, it's the inner loop. So beta gets indexed next. Beta goes from 1 to 2. So now we go and we have this global degree of freedom 21 associated to alpha equals 1, n equals 16. And this global degree of freedom associated to beta equals 2 and n equals 16 is going to be 43. So we're going to be updating entry 2143. We're going to use whatever was previously in there for 2143, and we're adding on this local stiffness matrix entry A1 to 16. What is A2143? A2143, well, there's 21, and it has this support, right? And where's 43? 43 is this guy here, which has these triangles as its support. So let's take the intersection of the supports of those two. That's what's important for computing this global entry. Well, it's going to be these two triangles are going to appear in the support, in the intersection of the support for 21 and 43. So it's over these two guys that we need to take a computation in order to compute A2143. A2143. We're only at this point adding in the contribution for triangle 16 because we're indexing through the triangles. We previously have already added K15 because n equals 15 comes before n equals 16. So we've already added that part in there. So that part is already in what was previously computed there. All we're doing is adding on the new piece of information, which is the local contribution coming from this triangle. Again, it's probably not going to make much sense until you actually write out and do an example. And now let's index beta again. So we get beta equals 3. Alpha is in the outer loop, and this is the outermost loop. N equals 16. Those are fixed as this guy indexes. So this is our global degrees of freedom, 21 and 42. Okay, 21 and 42. All right, again, so if we think about what A2142 means, it's going to be an integral involving these two basis functions. So we need to find their intersection of their supports, which is going to be precisely 14 and 16, right? Take the intersection of supports. We're adding in this contribution. This contribution has already been added in. So it's already going to be present in this calculation. We're simply adding in this piece of information coming from the basis functions with local degrees of freedom 1 and 3. Okay, so you can continue in this fashion. Now, how do I do piecewise quadratic? Well, piecewise quadratics involve a bunch of local quadratic functions, as you might expect. But in local quadratic functions, we're going to have 6 degrees of freedom, not 3. We have 6 degrees of freedom, not just 3. And you can see that pretty quickly. Remember, piecewise quadratics require that we number these, or we make as degrees of freedom these edge midpoints. So here's an edge midpoint, here's an edge midpoint. Now notice in triangle 14, this edge midpoint node is local degree of freedom 5, and in triangle 16 is local degree of freedom 6. This is a common feature. These things don't usually line up. They don't align. Now sometimes they could. For example, this could be the 4th degree of freedom in both the local ways of numbering. But usually they're different. Usually it's something like this. It's 4 in this 39 global degree of freedom is 4 over here, and it's 6 over here. Okay? So how a global node number is numbered locally is dependent upon the convention that we choose for the mesh that we construct at the very beginning. Let's take triangles 15 and 16 here. Okay, so that is that triangle and that triangle. So this is a similar mesh to what we had before. And all that has changed is now instead of having degrees of freedom at the vertices, we also have at these edge midpoints. Okay, and so for triangle 15, we now have this information. Local degree of freedom 1 is actually global degree of freedom 22. Okay, then we have 24 and 64, 24, 64. Then we usually count like this, 1, 2, 3, and then we come back, and after 1, we're going to go 4, 5, and 6. Okay, so 1, 2, 3, 4, 5, 6. Again, always in clockwise order. We could have done it differently. We could have said this is 1, 2, 3, 4, 5, and 6. Why do we keep this numbering that we've chosen here? Well, because the local node numberings of the vertices are still the same as they were in the piecewise linear case. So that's one reason why we do this. We don't have to. All you have to do is choose a convention and stick with it. Okay, so local node 4 is global node 23. Local node 5 is global node 40. Local node 6 is global node 39 for triangle 15. 16, of course, is similar. It should be, let's see, it should be 22, 64, 62, 39, 63, 38, which is that column there exactly. So this is how we do the same thing for the piecewise quadratic case. We need a little bit more information. I talked a little bit about the basis functions for the piecewise linear case, and the piecewise quadratic case is similar. It's just that they're not as easy to draw. Okay, so I'm going to simply define these guys and what they look like for both of these cases, but I'm going to use a simplifying methodology for doing this, which depends on what are called barycentric coordinates. But before I do that, I'm going to take a little break here and I'll take your questions. Okay, now I want to talk about a useful tool for doing calculations, and it's based on the concept of what are called barycentric coordinates. And you may or may not have seen this before. It's a rather simple idea, but it's useful and powerful. Suppose that I've got a triangle here. Okay, so this is some triangle K, and it's got local nodes A1, A2, A3. So these are actual, they're global coordinates, but they're numbered in a local fashion. Let X be any point in this triangle. X be any point. And actually, we can remember a triangle is open, so we can let it be any point in the closure. Now, that point actually divides the triangle into three subtriangles. And the way you do this is just take the point wherever it is and connect the three vertices to that point. Okay, this can always be uniquely done. If I'm here, then I'll connect these vertices this way. I get three triangles. Now, triangle K1 is going to be the one which is going to be opposite of A1. K2 is opposite of A2, and K3 is opposite of A3. The barycentric coordinate of that point X, okay, the ith barycentric coordinate is just the triangle, or is the area, or is the measure of triangle KI. So for example, if I'm talking about the barycentric coordinate 1, so I equals 1, so that's going to be the area of this triangle relative, created from this point X, divided by, and that's should be the area of triangle of the whole triangle. Okay, so this is a proportion, right? Because this is definitely some subset. It could be all of K, in which case that would be the point X is right here at A1, and so K1 takes up the whole domain, and so lambda 1 would just be equal to 1. Or it could be as small as 0, and that would be the case where A1 is somewhere on this line here. And it's going to give us a triangle which actually is degenerate and that has 0 area. Okay, so these are the vertices. This barycentric coordinate is computed relative to each one of these three vertices via this formula. Now, for A1, it's clearly equal to 1 whenever X is equal to A1. That's because in that case, the point X is here, and so this triangle K1 is the whole triangle. So the area of K1 over K is 1. And likewise, whenever lambda is, or sorry, whenever x is equal to a2, okay, so that would be, you kind of take this point x and you're going to keep pushing it further and further over here. Well, that triangle gets smaller and smaller, so lambda 1 is equal to 0 at this point, and lambda 1 is equal to 0 at this point for the same reason. So in general, these barycentric coordinates satisfy lambda I evaluated at aj is equal to the Kronecker delta symbol delta ij. Kronecker delta symbol is the most important symbol in finite elements, perhaps. All right. Now, what is really important here are lines, the isocontour lines of these lambda symbols, these barycentric coordinates. Now let's spin this triangle a little bit, or maybe look at a different triangle where A1 is up here, A2 is here, and A3 here is here. Again, we're continuing our tradition of numbering the nodes in counterclockwise order. A1, A2, A3. What are the lines where a or lambda 1 is equal to a constant value? Well, all along here, lambda 1 is going to have the value 0, because if I think about it, I'm going to make a triangle, right, which becomes more and more degenerate. And so its area is basically 0 if if x is here, because that triangle is degenerate. It's got no interior area. Lambda 1 is going to be identically equal to 0. Now, for any x that's on this line, that's a triangle of this length. A little formula tells us if this is 1/5 of the height up, then that triangle is going to be 1/5 of the total area. So that has the barycentric coordinate lambda 1 equals to 1/5. Let's go up to this line. So a line here where x is 2/5 of the height up. And you're just going to use the very simple formula, area equals 1/2 the base times the height. But now we're going only 1/5 of the height, or 2/5, I guess, for this line. So that's that triangle. Okay, the area ratio for that one is just going to be lambda equals 2/5. And so on. If I keep going, this is going to have an area ratio of lambda 1 equals 3/5. 4/5, and then this guy up here, if I take x to be up here, then the K1 triangle is the whole, right? It's the whole triangle, and so the ratio of areas is going to be 1. So these are the isocontours for this lambda 1 function. So notice it's 0, 0, and then 1, right? So that's the Lagrange nodal basis function that we had previously. Lambda 1 is the same as the Lagrange nodal basis function, psi 1. Okay, so we already said that. Lambda, in fact, lambda I is equal to psi I. Here's another, so we already observed this, that each one of these are fractions between 0 and 1. If you add up the areas of all the triangles, right, K1, K2, K3, you get the total area of the triangle. So if I add up these barycentric coordinates, it always has to add up to 1. Another interesting property. But it's clear it should be that to get these basis functions, they're simply equal to the individual barycentric coordinates, right? I hope you can see that. So this guy here is going to be 1 here, and it's going to be 0 there, and 0 here, right? So that's just going to be a little plane, right? Okay, so if I look at lambda 3, not lambda 3, sorry, but psi 3, it's equal to that. And that's exactly equal to the barycentric coordinate, the value of the barycentric coordinate, lambda 3. Let's do the quadratic case. So for the quadratic case, what do you think the local basis elements look like? Well, remember we said that they have to satisfy that if I evaluated local node A3, I should get, let's see, psi 3 at A3 should be 1, and it should be 0 at all the other guys. Okay? So let's think about that. Suppose we want to look at psi 1. Psi 1 is going to be 1 here, and it's going to go down like that, and it's 0 at those guys, and it's going to be 0 at these guys. So it should be 0 all along that line, 0 along that line, and so that's what it looks like. So how can I write psi 1 in terms of my barycentric coordinates? Lambda 1 and lambda 2 and lambda 3. Well, it turns out psi 1 is just equal to 2 times lambda 1 times the product, or the times the difference, lambda 1 minus 1/2. Now, why is this true? Well, let's think about it. Suppose I put in x equals a1. So x equals a1, lambda 1 at a1 is 1. We already said that. And so it's a 1 here. So I have 2 times 1 minus 1/2. So that's exactly equal to 1. If I put in a6, what do I know? Well, lambda 1 is equal to 0 at every, well, no, that's not true. Lambda 1 is equal to 0 along that line, okay? So if I put in a6, well, that's that guy there. Well, notice that it's on the line lambda 1 equals 1/2. So remember, it goes lambda 1 equals 0, lambda 1 equals 1/4, lambda 1 equals 1/2, 3/4, and then finally 1. So lambda 1 is equal to 1/2 as it is here at a6. That's going to kill that part because I'll get 1/2 minus 1/2. So psi 1 at a6 is equal to 0. Likewise, at a4, it's going to be equal to 0 because that's also on this line lambda 1 equals 1/2. What about these guys down here? Well, each one of those are on the line lambda 1 equals 0. Lambda 1 is equal to 0 for a3, a5, and a2. So it satisfies what I want, right? It satisfies what I want. That, well, let's see, I'm going to write it in general down here. Psi I at aj is equal to Kronecker delta ij. Okay, but that's just psi 1. Psi 1, it's defined the way you would expect it to. It's defined so that it's 1 here and it's 0 at all the other nodes. Okay? That's psi 1. What about psi 2? Psi 2 should be 1 here, and it should be 0 at all the other nodes. So let's see if it holds up if I do that. Well, by the same logic that I just showed you for this one will also satisfy, it's 1 here, 0 here, and 0 here. Why is it 0 here? Well, this is just going to be lambda 2 equals 1/2, so that part gets killed off there. If lambda 2 is equal to 1/2, that part goes to 0. If lambda 2 is equal to 0, this part gets thrown away. That's just 0. And whenever lambda 2 is equal to 1, I have 2 times 1 times 1/2. That's just 1. So again, I have psi 2 at aj is delta 2j. It's only equal to 1 whenever 2 is equal to j, or j is equal to 2. And likewise, psi 3 is given by barycentric coordinates in this same way. And notice that it has a nice symmetry. All these guys have the same sort of structure. That is the same as that is the same as that. All I'm doing is rotating this index around. Now, the bubble functions are different. The bubble functions, the local bubble function should be 1 at an edge midpoint, and it should be 0 at all other points. So let's see how this works. Well, let's see, this one, do I cover that? Maybe I don't exactly cover it. So we've got 4 minutes, so let's cover this one. Psi 4. Psi 4 should be 1 here, and it should be 0 at all the other nodes. This one, this one, this one, this one, and that one. All right, so what about psi 4? Well, psi 4 is exactly equal to lambda 2 equals 1/2 and lambda 1 equals 1/2. Okay, that's how I can describe it, right? lambda 1, 0, lambda 1 equals a half, and lambda 1 equals 1. So A4 is lambda 1 equals a half, and lambda 2 equals a half. So that's one way of expressing that point as a coordinate. Lambda 2 equals a half, lambda 2 equals 0, lambda 2 equals a quarter, 3/4, and then lambda 2 equals 1. Okay, so this is precisely the point. Lambda 1 equals a half, lambda 2 equals a half. And also, it's lambda 3 would be 0 in that case, right? Because it's on that line. Okay, so if I know that lambda 1 and lambda 2 are both a half, and I put in x equals a4 at that well, if I put in x equals a4, I know that lambda 2 is a half, lambda 1 is a half. So this is a half times 4. This is going to be equal to 1, the product, right? At that point. What if I put in, let's say, a2? Well, a2 is on the line lambda 1 equals 0. So that guy is equal to 0. Same with a5 and a3. Lambda 1 is equal to 0 at all three of these points. So that takes care of this point, this point, this point, and that point. 1, 0, 0, 0. What about these points here, these three? Well, these are all on the line lambda 2 equals 0. If I put lambda 2 equals 0 by setting x to be any point on this line, actually, I'm going to get 0. So this bubble function is 0 on this line and 0 on this line, and it's 1 here. Okay? And then you can find out what its values are on any line like this. So if I fix lambda 2 to be equals a half, then the value of this just varies like the value of lambda 1. Same with phi 5 and phi 6. You can argue those in a similar way. So these bubble functions look like something like that, and then they kind of look like that. Okay, so all in all, the reader can confirm that we have psi I aj is equal to Kronecker delta ij. I and j equals 1 up to 6. Okay, so our local stiffness matrix in this case is going to be a 6 by 6 matrix that has 36 elements in it because it's got 6 degrees of freedom, right? And we have to pair them up in all the possible combinations. It turns out that this is a local basis for P2, and we're going to prove this result in a little bit. But what that means is if I have any V, a polynomial of order 2 on a triangle K, there exists unique constants C1 through C6 such that V can be written as a linear combination of these basis functions. Now this is the Lagrange nodal basis, and it has a very nice property. And the property is always that these coefficients in this basis expansion, when I'm using the Lagrange nodal basis, are precisely equal to this. Cj is equal to, oh, this is a typo here. There's no hat on that. Okay. So Cj is precisely equal to V evaluated at Aj. And that just that holds because of this relationship here. If I put in Aij for x, then I get a Kronecker delta symbol, and so out pops, if I said putting in Aj here, out pops Cj. Or maybe it's better to think about it as putting an AI here. What pops out is going to be CI. Okay, so try it out for yourself. And the fact that this is a local basis, we're going to prove kind of conclusively in a moment. Well, not in a moment, but next time we meet. Okay, so that's where I'm going to end the lecture. And you can turn your cameras on and I'll take your questions.